Okay, so our next video is all about thin film interference. And it's not an easy topic, this one, but there's going to be a few little things that you always want to try and consider, some things to make note of when trying to solve any thin film interference questions. So the first thing is, when we're talking about a thin film, we're really looking at reflections, or two reflections really, that are taking place. So we're always going to be following our line coming in. So if we're looking here, we've got to look at our line coming down, and we've got a reflection off the first boundary. So I'm going to call that line A. Okay, I then have some of it gets refracted inside, and then gets reflected off our second boundary and then refracts back out, and that would be path B. So we have path A and path B. Now in this case, for example, I'm going to have like air is usually always going to be in our questions starting from air, entering our thin film. So that could be something like soap, it could be oil, it could be a special type of chemical that they use on coatings, on lenses. And then our next one underneath is going to be our material. It could be air again, like in the soap bubble. It might be water or oil. Lots of different things that it could be. And when we're looking at this then, so there's a few of the things that we want to consider, is we're going to have to talk about the lambda on the outside. We're going to have lambda dash, and that's our wavelength in the middle. Okay, because our wavelength in the middle is going to be different because, again, with Snell's law, we know that the wavelength changes as it enters a new medium. And I also want to know about the size of my thin film. Remember, it's thin, so it is going to be usually very small when we're talking about it in terms of meters. And we're going to label that as D. The other things as well to consider is our refractive index. So refractive index of 1, the refractive index of 2, and the refractive index of 3. So just to kind of recap, we've got path A, that's light reflected off our top boundary. B, light is refracted and then reflected off the second boundary and then emerges back out. So the first thing to kind of consider is path B has gone further than path A. Okay, it's gone inside and then back out, whereas A has just done this. Path B has done a little bit extra, and we can call that path difference in the middle 2D. So the path difference between A and B is equal to 2D. Okay, it's actually, if we look at this in terms of like our algebra, okay, it's actually technically a little bit more than 2D, but because we're dealing with very, very small angles, we can say that we end up with it being D. Okay, so that's one thing to make sure we know. Path B has travelled further than path A by a path difference of 2D. Okay, so that 2D is our path difference between the two, and that's something that's really important for us to know about. The other thing that we always want to think about when we're looking at a question is we want to always consider the phase change of the reflection. So remember, we have a reflection here, and we have a second reflection here. Okay, and this is the phase change that is taking place at these two boundaries. Now, this is going to differ depending on what type of question you have, but you want to always look at, is it going from a more dense medium to a less dense medium? Or is it going from a less dense medium to a more dense medium? Now, if it's going from more dense to less dense, then there's no phase change. So for example, let's say I was going from air, not wrong way around, I should have said that, I'm going from glass into air. Okay, I'm going from more dense to less dense. So if my path moved along, it's going to reflect back with no phase change. Okay, so we can see it reflects back exactly the same as it was approaching it. Okay, we can also remember some of it is going to partially refract through. If though it's going from less dense to more dense, then we're actually going to have a pi phase change. So again, let's say this time we are going from air into glass. Okay, so less dense into more dense. Oops, sorry, you can't quite see that. This time round, the reflection is going to be pi out of phase. So we have a pi phase change there. Okay, so you can now see it's doing the opposite of what it was approaching. And again, we have some just continuing on. So I've just cut those dotted to show parts that are being refracted into the material. So these are the two little questions that I need to be asking myself. What is the phase change at each boundary? Okay, so what's the phase change here compared to what is the phase change here? All right, so Is it more dense to less dense or less dense to more dense? These you need to learn. You need to make sure you look at those, that you write them down, that you repeat them, so that you know less dense to more dense, pi phase change. More dense to less dense, no phase change. Okay? So we're going to look at some constructive interference, and I'm going to be using the example of going from less dense to more dense to less dense. I'm going to use the soap bubble for this. Okay, so this is constructive interference when we're going from less to more. Okay, so less to more, back to less. So air to film to air. Okay, so this is this one. Again, this would be different for different questions. So for constructive interference, I want A and B to both meet in phase. So a peak meeting a peak. We want them to peak and the peak to make a bigger peak. Okay, so A and B must be in phase. So then I look at them and I look up here. So I go, right, path A, okay, up here, this has had a pi phase change. We've gone from less dense to more dense. I look at path B. Well, path B is going more dense to less dense, so there's no phase change. Okay. Now, to get constructive interference, I've now got this being pi phase change, and this now is out of phase with pi B, so with line B. So to make this approach and be back in phase together, the path difference becomes really important here. Okay. So I need to have a path difference that helps me make my B become pi out of phase so that it will approach back in with A. So in this case, I need to have my path difference in multiples of a half lambda, okay? This has gone through, there's no pi change over here, so essentially for this to equal the opposite as before, we need to have a multiple of a half lambda in between. Now, remember here, I'm using this line dash because I'm talking about the lambda inside, okay? The wavelength outside is just lambda, okay? So lambda inside here, so lambda dash over 2. So what I want to say then is that 2D, my path difference, must be equal to some multiple of a half of lambda dash, okay? Well, using Snell's law, lambda dash over lambda is equal to n of air over n of the film. N of the air is equal to 1, so we can ignore it. So I can rearrange and say lambda dash is equal to lambda over n film. Well, in this case, 2D is equal to m plus a half. If I substitute in lambda over n film, I can then say 2dn is equal to m plus a half lambda. Okay, m is just our number of waves. So for example, if I'm looking at the film that is travelling through, has it gone a couple as it goes through? So I'm looking at how many multiples of wavelength it's travelled between. Okay, so we can start at 0, we could have 1 wave, we could have 2 waves as we're going through there. So it's just how much wave is moving through the material. So that's for constructive interference, for when we're going less to more to less. For destructive interference, I need A and B to be pi out of phase. Now, we already know A has a pi phase change and B has no phase change. So they're already pi out of phase, which essentially means my path difference in the middle, I just need them to stay exactly the same type of wave. I just need the exact same amount of wave to go through. Okay, essentially, I just need it to stay in multiples of their own wavelength, multiples of lambda, so they can stay being pi out of phase. So in this case, we end up with just 2dn is equal to m lambda. I don't need that extra half to make it out of phase now. So 2dn is equal to m lambda for destructive interference. Okay, so again, we want them to be out of phase, so a peak meeting a trough, so that they become cancelled out. One of the little questions that's often kind of used in the exams when I've been looking through past paper questions is often things like, why do lenses have thin films? Or why do we use thin films in like cameras or on lots of different things and surfaces? And the main thing here is that we're reducing reflections. We're reducing glare, okay, because of destructive interference. If these reflections coming off the thin film are becoming destructive, they cancel out, which means we reduce lens flare. So that's just a little one that I've seen pop up in lots of questions. I'm going to do a little example, just so that we've got a little one here. But again, it's not an easy topic. I would suggest practicing practice questions and ask me if you need any help. So the first one says, what is the minimum thickness for a soap bubble that gives constructive interference for a light source of lambda inside of 550 nanometers inside of the soap? So usually at this, I'm going to draw it out and I'm going to just sort of think what's happening. So I've got my air, it's going and reflecting off. Now, less dense to more dense. So we have a pi phase change, just to repeat so that you can keep remembering that. Some of it reflects inside, so refracts inside and then reflects back off the bottom boundary and then refracts back out. Again, more dense to less dense. So again, we have 0 phase change there. Now, because I'm doing that less dense to more dense to less dense, I'm going to use my constructive interference equation, which is this one here. Now, at this time round, I'm going to look at what I've been given. I want to find out the minimum thickness. So I want to see the least amount of phase change happening. So I'm going to be looking at the smallest m possible. Okay, in this case, that's m is equal to 0. The other thing that I've been given here is I've not been given this lambda. I've actually been given the lambda dash, the lambda inside. So the lambda inside of the soap. So I'm going to go back, rather than using this equation, I'm going to go back to my original equation, which is 2d is equal to m plus a half lambda dash. Okay, again, my n of my film, because that becomes lambda is equal to lambda n of the film, the two n films cancel out. Again, we then solve through, d is equal to m plus a half lambda over 2. Well, in this case, m is equal to 0, so d is equal to a half lambda dash over 2, which is equal to a half 550 nanometers, so times 10 to the minus 9 divided by 2. So in this case, 1.0 times 10 to the minus 7 meters. Okay. Again, please let me know if you do need any more help with this.